This is the winter break project with the poster, and it's basically a review of what we did first semester. We got two diagrams here. The one on the left is constant velocity with a man pushing a block, and
Uh,
it's moving in the positive direction. Uh, it's moving at a constant velocity at 2 meters per second, and constant velocity means it's at the same speed but not speeding up or slowing down. It's constant, stays the same. And the position time graph will just be a straight diagonal line, and the slope means the slope of the position graph is the velocity, and in the velocity time graph it's a horizontal line of what the slope of the position graph is. So since it's the slope is 2 meters per second, the velocity is going to be on the 2 going horizontal, and the slope is the acceleration, uh, and the area of the graph is displacement, which is final position subtracted with initial position. And the acceleration graph is on zero because there is no acceleration. It's not speeding up or slowing down. It is moving at a constant speed. I guess
uh,
that's it.
Eric, before you go on to the force diagram, let me explain a little more what the slope means. Uh, for the position time graph, the slope means the slope is 2 meters per second. That's the slope for the position time graph. So every second, the box would move 2 meters, and yeah, it's basically. I just want to alliterate on that.
Oh, okay.
All right. So since the guy is pushing the box in the right, there are going to be four forces acting upon it. Uh, Down would be weight, so that's basically gravity. Up is the normal force, so that's the force of the surface. Um, to the left would be friction, so that's the ground acting upon it again. And then there's the applied force, so that would be the man pushing it. So when you put these uh, vectors together for the vector sum diagram, you will get that rectangle there. The And it'll be put tail to head for each one. And since it is constant velocity, there's going to be a zero net force. So the sum of all these forces are going to be equal to zero.
Same thing if there's no acceleration. If there's no acceleration, there's no net force.
Yeah, that's accelerate. No acceleration is constant velocity. Yeah, Jensen,
Okay,
constant acceleration.
okay, the constant acceleration. It's basically an object that is speeding up constantly or slowing down constantly. So it's compared to the velocity time graph. No, constant velocity. This time it's actually just speeding up now. And in the position time graph, it's showing that it's slowing down over time as it goes farther. And this and it's slow and in the graph it shows here that it's slowing down in the positive direction but speeding up in the negative direction because of our diagram, as you can see in the top. For the velocity versus time, we can see that the graph is going down, or the slope is going down, because we're going in a negative direction, speeding up. Therefore, the slope velocity times it's showing that it's going in a negative direction, and it's also and the area of the velocity time graph is the displacement or the change in position. Acceleration versus time graph. We it's showing that it's constant because over time we speed up this amount of numbers, and so the acceleration, it cannot be zero since we are constantly accelerating based on the velocity time graph. And if we want to do the area of the area of the acceleration time graph, it is the change in position, change in velocity, and yeah.
Okay, so the force diagram for that one is almost the same as the force diagram for the constant velocity. except that now the force of friction is greater than the force of sorry, friction is less than the applied force, so that will allow the box to move at an increasing speed, so accelerate. So what that means is when we plug it into the vector sum diagram, the applied force being more than the friction would result in there being a net force in the negative direction, so that's to the left. So yeah,
So there is an acceleration.
there's an acceleration to the left of, what did we get? Negative 0.8 meters a second. So the negative 0.8 is, it's the sorry, what we got for the acceleration versus time graph is negative 0.8. So what that means is basically an acceleration of negative point of sorry, not negative 0.8, 0.8 meters a second per second in the negative direction.
Got it.
All right. I'll explain the, what do you call it?
Third law.
Newton's third law part. So basically, our scenario is that the two people are pushing the boxes towards each other, and that we have it where they meet after 5 seconds. They'll hit. That's why we see in the position time graph that it only goes up to 5 seconds, and the position time graph for the constant acceleration graph goes from position 20 to 10, because it'll travel 10 meters. So after they travel after each travels 5 seconds, they'll meet, and once they hit, they begin to apply force on each other. The force they apply on each other is equal according to Newton's third law, because basically the law says that in any interaction between two objects, the force the objects apply on each other are always going to be equal. So the force box 1 applies on box 2 is the exact same as the force block 2 applies on box 1. And that's basically it.
Is it?
Is it, Eric?
You should.
Are we done?